Welcome back. This is a lecture on pedestrian crowd and evacuation dynamics. And if there are any questions or comments, please dare to interrupt me. We want this to be interactive. And also, if you're following this online, Sachit will alert me if there's a hand up or if there's a comment, okay? So today, I will start with a discussion, so that's going to be definitely your part. And then I will go into observations and empirical evidence, some scientific puzzles. Then we'll discuss how to model pedestrian flows. I will look into simulations of self-realization phenomena. We will talk about crowd disasters and how to prevent them, and there will be take-home messages, hopefully to be remembered. So now your turn. What do you know about pedestrians actually? Yes? Try to avoid each other, right? Most of the time, yes. Right, so that was in London, right? This famous bridge is just next to the Gallery of Arts. Yeah, that was synchronizing, swinging, yes. But that's a very unusual phenomenon and pretty much unwanted. So in fact, they had to do some fixing of the bridge afterwards. But yes, important observation, because in case soldiers are marching on a bridge in a synchronized way, it could actually make a bridge collapse. I think I've even seen a video sometime on YouTube or something. So yeah, from that point of view, it does have practical importance, actually. What else? Chaotic. Yes? Unpredictable. So then do you think we can model them at all?
Maybe roughly, but not usually but maybe not like this.
Okay. And here was a hand as well. Okay, that's a very good point. A comment, okay. Please speak up, open your mic if you don't mind.
Sorry, I didn't know we could just speak up, sorry. I don't know, maybe it can be described as a multiple particle system, but with actually not a randomized movement, but with the movement has some kind of intentionality or directionality.
So many particle system with some randomness and some intentionality, okay. Actually, we are already on slide, I don't know, 20 or so. So we're making very good progress and can go home early today if that continues this way. All right. So here are a few responses from a previous lecture. They tend to be in my way. Okay, they occupy some space as more or less the same thing. They have a target, go from A to B. They move more or less automatic, but they behave unpredictably at times. They have the highest priority because they're the most vulnerable traffic participants. And I'd like to continue the brainstorming a little bit more. So what else might be interesting? Yes?
It's not weird, or there are smaller and taller.
Smaller and taller, not uniform, diverse, yes.
Many groups.
Groups, yes. Yes.
It can also depend a bit on the country we're in. There's a bit of cultural differences on how people react to the traffic and how they organize themselves.
Cultural differences, how people react to each other, absolutely.
The velocities, some are slower, some are faster.
Can you speak louder, please?
The velocities, some are slower and some are faster.
Some are slower, some are faster, absolutely. Yes?
The behavior might change in problem. A lot of people
So what do you want to say? Density matters. Okay. Absolutely so. So here are some responses from a previous lecture. Diversity of behaviors needs to be considered. How to design infrastructures and how do they guide people, or how can they be built to guide people? Why do crowd disasters happen? How to avoid them? How to manage crowds? And how to reduce crowding and risks. Now, quick overview, we'll talk about self-organization at some lengths. We'll talk about large-scale simulations, and we'll now go into empirical approaches. But actually, before we do that, I'd like you to look a little bit more on this slide. Do you notice anything over here? Yes?
Couple.
Two men sort of flow here, one going in that direction, the other in the other direction.
So the two opposite flow directions are separated from each other. Which city is that? London, yeah. So where do buses go in London?
Walking opposite compared to the street, so
Left or right?
to the right.
Left. Buses buses and cars go left, but pedestrians here, I think it's Oxford Street, go right. We'll remember that, okay? All right, some empirical approaches. And of course, all of that is about observations. It's very interesting to go out and watch crowds and how they behave, because there are some interesting particularities. You know what place that is? Paris, Centre Pompidou is right over here, and you may recognize this. And there's a street artist who basically is entertaining the crowds, and that creates those circles, and people have to walk in between the circles, right? And then over here, you see standing people and moving people. And of course, that is important to consider. Now, the earliest approaches, perhaps in terms of modeling pedestrians or quantifying their behavior, go back to Professor Froome, and he introduced a level of service concept. And as you can see over here, he's basically distinguishing different density levels and describes the particular conditions that people find. Level A is kind of the highest level of service. There's sufficient area available. People can basically freely select their own walking speed, and there are basically no conflicts with other pedestrians that can be avoided. And then it goes up to level B and C and D, E, finally F. F is the worst condition, and over here we see a complete breakdown in traffic flow with many stoppages. Movement speed is entirely dependent on the person in front. Okay. And you can do this kind of analysis not only for walkways, but you can do that also for stairs or for queues. And basically, level of service is somehow related to the comfort of the pedestrian facility or of the conditions that pedestrians are facing. And you shouldn't go beyond level B, I would say. Now, there is another very important approach, which is the fundamental diagram, and you probably recognize this name. Ulrich Weidmann is also at ETH and did this very famous work. So here you can basically see how speed relates to density, how flow relates to density, and how flow relates to speed. And as it says, this is called the fundamental diagram. The average speed is around 1.3 meters per second. Free speed, I should say. And these kind of data are then being used to plan infrastructures, in particular pedestrian facilities. And there's a highway manual that had these kind of spreadsheets where you could fill in numbers and calculate the required width of a walkway, for example. This is kind of the old ways, right? And we'll see how we do it today. Of course, we're using computers for computer simulation and so on. But the question is how to do that, right? Those forms were basically using regression curves. In many cases, even linear regression curves, right? A very simple approach. Today, we have much more sophisticated approaches. So this was about density and flow, and these are surely important, but wouldn't the dynamics be even more interesting? Now, I got interested in this back when I was in Göttingen. I studied over there. And what you see over here is a monument called Der Nabel. It's kind of in the center of the city. And as you can see, people are sitting here. And I was sometimes one of them because I decided I wanted to know more about real pedestrians. And so I thought it was important to leave the lab and observe people as they behave in reality. And what came out of this was a diploma thesis, and here is the title of it. And it was basically reporting about a number of phenomena that I found. One of them was, in fact, this separation of opposite walking directions into lanes of uniform walking directions, something that most people don't even notice. I mean, it's there, but most people don't pay attention to it. And it's there basically in every city. I would even claim we would find that in places where people have never used a car. Because as we will see, it's really a result of the interactions between people and not about the traffic laws of the country or so. Then I came to distinguish basically different states of pedestrian flows inspired by physics. I mean, obviously I had studied physics at that time. And so it was natural to assume a gaseous state where basically there were little or no obstructions, low densities. I was, as a proper student, of course, I was also going out to a discotheque to go dancing, and there I observed basically this phenomenon, that the density of people on the dance floor was typically much smaller than the density of people standing around and watching. So I was wondering, could we understand that as a matter of that the pressure of both faces had to be the same to have a stable configuration. Now, pressure is proportional to density times velocity variance. That means if the velocity variance is large, as is the case on the dance floor, the density would have to be lower to basically have the same pressure, a pressure equilibrium.
There's a question.
A question, okay, please speak up.
Does this pattern emerge everywhere on the webpage, or does it make a difference whether it's a shopping street or a purely transition?
Purely what?
Transitions.
What is a transitional?
So basically a street where a street that's really only for transition or getting from one point to another.
Well, I would say we see it in both situations, but the shopping setting basically also comes with window displays that attract people and would make them stand around and stand in other people's way. So kind of the shopping situation is a little bit more complicated, but I have seen the separation of lanes of uniform walking direction basically in many pedestrian zones where you do have the shopping going on. For sure, it's happening in those transitional situations that were mentioned by you. Yes?
I asked if people that these two lanes separate.
If there's a very low density, I think there's no benefit of a separation because there's enough space anyway. So I would expect that this is for sure at least more pronounced under conditions of higher density.
It depends on the
Yes.
interactions, right, between pedestrians.
Dance
Sorry.
floor, why do we assume that pressure is the same?
Because otherwise the interface between those two faces would move. Right? If the pressure is higher on one side, then basically there is a non-stationarity of the situation. That's at least what is expected. We'll later on see that the pressure really is important. Okay, and then I noticed those footprints in snow around obstacles, and this reminded me somehow of streamlines of fluids around obstacles. So I hypothesized basically a fluid state as well. In fact, there are some interesting phenomena going on. Over here, we'll see a crowd of people waiting in front of a cinema room. And after some time, the show ends and people are leaving the room. I will see the formation of a river-like stream of people moving out. And then we see two shock waves as the crowd tries to get inside of the room. So shock waves means sudden, abrupt movements. And you can imagine that potentially that could be dangerous. Then also it could happen that the densities get so high that basically, even unintentionally, there would be body contacts between people and forces would be transmitted, and that is a situation that somehow has similarities with granular media. So first summary of observations, there are gaseous, free, fluid, with obstructed, solid states where basically people cannot really move a lot. The footprints in snow look similar to streamlines. Passing through a standing pedestrian path leads to river-like streams. In bushy pedestrian paths, one can observe shock waves. And then there are similarities with random media at high pedestrian densities. Okay. And now let us focus on emergent phenomena, on self-organization, on spatial temporal pattern formation. Personally, I find that extremely interesting. What happens when people interact with each other and something happens that was not directly intended by the individual, but comes about through the interaction of many individuals. And among these phenomena is the lane formation that we have already discussed shortly, and we will come back to this perhaps even a few more times. In particular, we'll come back also in the game theory lecture to understand why there's a preference for one side. There's a behavioral convention, so to say. And in fact, that behavioral convention is culture dependent. Perhaps culture is not even the explaining variable, but what we can see is that in some countries, people tend to walk on the right-hand side, and in other countries, they tend to walk on the left-hand side, as I've observed, for example, in Japan. This is very interesting and also important to distinguish between different possible explanations of that phenomenon. Over here, we'll see a video recording that I made in Budapest. I have done video recordings actually many places. I've seen that phenomenon really everywhere. And then one day there was an opportunity even to make an experiment with many students in Dresden. And here you can see different configurations like a short bottleneck, a long bottleneck, unidirectional flows through bottlenecks, bidirectional flows through bottlenecks. And what we find basically is that there is some oscillatory movement. That means the bottleneck tends to be passed by a number of people and then in the other direction by a number of people. It's not just one by one. So there's another self-organization phenomenon. You see it slightly in that video. I always hope that somebody would take a better one. Because I've seen that also at museum entrances and so on. So we should basically focus on this side over here. Then I think it's becoming a bit visible. And I also, of course, observed the situation in the underground station, and over here, the pressure principle, in fact, plays an important role because the density typically is much higher in those underground vehicles. So first, there's a discharge, and then people move in. All right, so we also had a look at intersections and widenings. And I should just perhaps say that widenings are perhaps somewhat unexpectedly like bottlenecks. because people would use that space and then they want to get back in. And so the second part of the widening is actually a bottleneck, and it's a disturbance of the flow. So if you want to avoid that, it's better don't have those widenings. We made a quite interesting observation at intersections. Look at the intersection area. We'll see that most of the time people don't stop, but they just keep on walking, and they somehow manage to coordinate. And here is a sketch of a Japanese team of scientists who have apparently observed a famous pedestrian crossing that I'll show you later on. And this is their analysis, how people move. So the interesting point is that those two streams are organized in a way that we call stripe formation, that allows people to move through this other crowd without stopping. That means they can move sideward within the stripes, and the stripes move forward at the same time. And I found that really amazing, because I think I would ask people to come up with a solution for that problem. I'm not sure there would be a lot of people coming up with a stripe formation solution, but it just happens, like people do it without figuring out the math or doing an optimization problem. Yes? Discipline.
I don't know if you've seen videos, but there are videos of it's like a presentation. Massive amount of people on suits, they walk, they cross each other perfectly.
So you're saying basically they learn it at school how to do that?
I don't know, it's more of a competition style discipline. It's not the basic training.
I mean, is that true? Yeah. How is the situation? Yes, we'll see it shortly. It's really fascinating, and I've been there in person. Actually, it's an amazing place. All right, so here's another summary. People form collective patterns of motion, such as lanes, oscillations, and stripes. So there are different kinds of collective patterns. Those collective patterns of motion are culturally dependent, like the preferred side of walking, acceptable distance, and so on. The patterns tend to be quite efficient at normal densities. And somehow you could think perhaps of the principle of Adam Smith's invisible hand, something that we also call optimal self-organization. But there are some scientific puzzles. So how important is psychology? How important is sociology to understand the phenomena? What do you think? Is it important? And how important is it?
I think I don't know like how important it is, but I think different people have different ways to deal with situations, and maybe like, it has something to do with their experiences and everything. So I don't know how to put it in a percentage, but maybe.
Yeah, How does self-organization, how do collective patterns of motion come about? And we'll see that, in fact, the models that we will work out don't have psychology in them, and they still reproduce the basic findings. That doesn't mean that psychology plays no role, but kind of the most important effects may not be of psychological nature. Or what we actually do is we represent psychological effects by means of forces. When and why do efficient patterns of motion break down? And do we need to assume a planning and optimization of trajectories? I'm asking this question because some roboticists have been talking to me that they were very much interested also in the pedestrian simulations that we were doing. And of course, they want to build robots that can move through a crowd of people. And what they often do is they use kind of a visual system, like a camera system, that does pattern recognition and basically tries to extract the trajectories of everyone they see on that camera picture and try to extrapolate it into the future. And then based on those extrapolated trajectories, they're trying to solve an optimization problem, how to move through the crowd in an optimal way. And, you know, if you do it this way, you can really burn a lot of computational time. It needs a lot of processing power. The models that we have developed are much simpler and are surprisingly efficient. And so we're getting into the modeling approaches. So here, there are actually different kinds of models. There are micro level models, such as molecular dynamics or cellular automata that focus on the motion of individuals. There are macroscopic descriptions like fluid dynamic models, formulating similar formulas as, in fact, fluid dynamics and physics is using, or even more coarse-grained queuing network approach, where you just care about the number of people in a room and how that changes over time. While the fluid dynamics still looks at densities and average speeds, at least. And the mesoscopic level description is somewhere in between, which also cares about velocity distributions of people in space and time. And here are some more or less famous models. By far, not all of them. And it goes on and on and on, you know. And there are probably in the hundreds of different versions of models, but they are all microscopic, mesoscopic, or macroscopic in nature. And in the following, we'll focus on the social force model. It's probably one of the most used and most cited kinds of models. And this model basically assumes that people do learn how to behave more or less optimally when they're young. And so they learn how to walk around other people and obstacles and so on and so on. And they do that better and better. And eventually, some typical behavior results close to optimal that then can be put into mathematical formulas. And in this case, it has been assumed that this could be done through an equation of motion, which just describes that the location of pedestrian alpha changes with time according to the speed, and the speed changes with time according to an acceleration equation, and that is made up of a sum of forces. those forces would represent different kinds of effects, such as acceleration of the actual speed towards a desired speed and desired direction of motion, and that takes some adaptation time. And then there are interactions between pedestrians, typically repulsive, as you've already pointed out. But if there are families or so, or tourist groups walking together, then obviously there are also some attractive effects, or if there are window displays, it could also be attractive effects, but otherwise there would be repulsive effects of boundaries to keep some safety distance, right? And we could add also a fluctuation term to account for the variability in behavior. So basically, a focal pedestrian is being influenced by other pedestrians and by walls. And then there is this, as it was pointed out by one of our Zoom participants, there is this driving effect, this intentionality, which distinguishes people clearly from particles. And it's not the only thing, of course, that distinguishes people from particles, but in that kind of modeling, this is really important. Oops. So if you go into detail and specify those forces, then things start looking a bit more complicated. But the main point is actually that most of the time, as a scientist, you would study not the complexity of everything coming together, but you would study standardized situations in which, say, 2 or 3 of those terms matter, and everything else is basically excluded from the experiment. Yes? Yes, because the size of the strides that people make is speed dependent, obviously. It depends on kind of the detailedness or sophistication of the model. The simplest models actually don't take into account speeds or speed differences, and they still produce, interestingly enough, delay information phenomena and some other phenomena that are reproduced by surprisingly simple physics-style models with this desired direction of motion and desired speed, the driving force term, right? This is important. Okay, so then the question is how to specify actually those forces, and that has been done in different ways in the past. So when there was no data available, times before people had cheap video cameras, we just made assumptions and looked at whether the models produced some phenomena that looked similar to what was observed in reality. Then when there was some data available using video cameras, we hypothesized certain kind of mathematical relationships that have parameters in them like A and B, or delta t, which is here you see a speed dependence. So in the easiest case, where we would just have a circular potential that, according to a gradient, then defines a repulsive force, but we would also look at elliptical specifications that would be more sophisticated and take into account here relative velocities in an elliptical tube, for example, right? In any way, we take videos and we take simulations and we compare the two. And this is done in the following way. For each pedestrian. In the movies that have been recorded, the trajectories are extracted. And so in the computer simulation, we simulate the expected movement in response to the other people in that movie. And we do that for all the people. And then we compare the simulated position with the actual position. That defines an error. That error is being squared. All the errors are being summed up. And then what we want to do is to find the parameters in the model that minimize the overall error, right? And this way you determine the best fit of the model to the data. And what you see over here, that elliptical 2 actually performs best among those three. And then we have looked at another specification that actually the lambda that takes into account something like visibility is not symmetric. I mean, people see what is in front of them. They don't see what is behind them. They see a little bit is what is on their side, right? So there's basically we introduced a cosine factor, and that lambda corresponds to that. Okay, so video trajectories extracted, compared with the predicted simulation, the parameters, the optimal parameters were determined, and then we did computer simulations for different densities, and those stars over here correspond to the predicted flow density there. Later on, actually, we got into a situation where a lot more data became available. So we could take another approach, a data-driven approach in a sense, right? And over here, we eventually figured out what kind of model was actually fitting the data. We didn't have to assume a class of models. And so experiments were made in order to get that data. And first, people were studied single pedestrians in the corridor. And you can see that we put some table tennis balls on the shoulders. It made it easier to measure the exact movement of the pedestrians. And here you can see their acceleration behavior. In fact, their speed that they end up with is about 1.3 meters per second. As I mentioned before, it's about an exponential adaptation to the desired speed. And then the next thing that we did was to look at interactions between two pedestrians, and even more than two eventually. So one situation was one pedestrian moving, the other pedestrian standing. And there was the other situation of two pedestrians moving, okay? And then that produced quite a lot of data at the time when we did that study. And so we could basically figure out how people responded to another person depending on the relative position. What we found, and perhaps somewhat surprisingly, not only was there a preferred site on which they avoided other people, but the difference was actually amplified when both people moved. So there was a reinforcement effect, basically. And this is much more pronounced, right? a preference for the right-hand side if both people moved. And we could basically figure out an empirical force field. I mean, when I did my diploma thesis, I thought, oh, how wonderful would it be if you could determine the forces that are acting between pedestrian and social forces. But at that time, I couldn't imagine we would ever get into a situation where that would be possible. And see how technology has changed the situation. It has become possible. And so it has become possible also to determine those mathematical functions from the data. There are basically two components. One component is if you have a head-on movement, then you would decelerate to avoid a collision. However, if it's not exactly head-on, but a little bit sidewards, then you mainly change the direction to walk around each other, right? So you go sideways. These are the two components that are basically overlaid, and there's an exponential decay, as you can see. And if you then compare the force fields in the observation with those corresponding to the mathematical function fitting the data, then it gets pretty close. It's not exact, but still pretty close. And in particular, the average trajectory is clearly within the empirical trajectory plus standard deviation. But also we get the preference for the right-hand side right, and we can reproduce that this preference is more pronounced if both people move. Okay.
Is this related to magnetic flux density and the attraction repulsion of ferromagnetic particles?
Wow, ferromagnetic particles, and I wouldn't go so far, to be honest. We will see that actually there are some clear differences to fluids and phenomena in physics. It's nice to be inspired by physics, but then it's always important to see how well it can be transferred. So I think it's a good question, and I cannot finally answer it, but my intuition tells me that most likely it's not going to be that kind of phenomenon. What we then did, we applied, was it a question?
I mean, like we have like these problems that usually for water, like arise, a lot of particles around the speed. One particle is part of it. With this discussion,
Right. You're both studying physics, huh? No?
quantum engineering.
Quantum engineering. Oh, wow. Okay. So what's your verdict then? What's your verdict? Your judgment? Would you think this magnetic properties might be observed? I was skeptical, but how do you see it? Yeah, I agree. But yeah, it's good to ask these kind of questions. I mean, it's interesting. And so what we then did, we basically simulated a situation not only involving two pedestrians, but many pedestrians. And we're trying to predict the situation that we didn't calibrate the model to. And that was the situation shown over here with a walkway. and a lot of people in the pedestrian zone. As you can see, even though we didn't recalibrate the model, it was actually predicting the right distribution of people in that pedestrian zone. Okay, so it worked well. Also, what you find is those computer simulations are nicely reproducing the lane formation phenomenon. And actually, what is important here is the relative velocity. Each time two people meet, obviously they have to go a little bit aside in order to avoid each other. That happens more often the higher the relative velocity is. And that is why basically those opposite directions of motion are eventually separated from each other, and we'll get, in the end, the most stable pattern, which is if you have a sufficiently long walkway and enough people, high enough density, which is a situation with 2 lanes only. If you don't have a long walkway, you could have more than 2 lanes. But you would get that lane formation phenomenon, and at bottlenecks, we would also find the oscillatory flows that we talked about before. It looks a bit as if there was a traffic light over here, but it's not. There's no policeman. There's no laws that tell people to do this. It's just based on those interactions, assuming social forces among them. And as you remember, this has later on inspired our new kind of traffic light control, right? So here is finally the intersection I promised to show you, the one in Japan. And you can see this quite unusual situation that you also have kind of 2 crossing walkways. So for some time, the entire intersection is free for pedestrians. They can walk basically anywhere. Want to see it again? If you're in Japan, you have to do that. All right, and here is a computer simulation, and what you'll see in a few seconds is the stripe formation phenomenon. And it happens just based on this simple social force model that we formulated. So you can see stripes are the patterns that form. People walk sideways in the stripes, and the stripes move forward. This way, people don't have to stop. Yes? But that sounds like a more dangerous experiment. Interesting. Yeah, it makes sense. Yeah. And now the question is, given those findings that we made, does that have any implications for the way pedestrian facilities should be organized? And it turns out, in fact, they can be improved. So assume we have this intersection of 4 different walking directions. Then what happens is in the intersection area will be quite chaotic. So I assume chaotic was mentioned by people in the room, right? Here you really expect this to happen. And you want to get rid of the chaos, right? So what could you do? Well, we could subdivide the intersection into of 4 walking directions into 4 intersections of 2 walking directions each. And that's what we basically do over here. And in that case, basically you get the stripe formation phenomenon in each of those 2 direction intersections. And altogether you get this rotary traffic flow. And in fact, it turns out that this is improving the traffic situation, the efficiency of the flow. It reduces the mutual disturbances. But altogether, we can say that all the elements of pedestrian facilities, which are corridors, bottlenecks, and intersections, can be improved. Like the classical design is not the optimal design. It's clear for the bottleneck. If you cut away space to have a funnel-shaped solution, it's clear that this improves the flow, it reduces the disturbances that happen over here coming from people in the corners. So less is more. Interestingly enough, the funnel-shaped solution is better. And once you have understood that, you could start thinking, okay, if we take away space over here by putting some obstacles into the way, inspired by that underground station, would that improve the flow? And in fact, it does, because it helps to separate the flow directions. And here is actually a situation. Now everyone is coming towards us. A train has arrived. People are now also walking in the other direction after some time. Basically, you have a separation of the flow directions, and the pillars help to support that separation effect. But it's a transparent solution, so it's adaptable. That is a good thing. And then finally, we thought, okay, what happens if you put an obstacle into the intersection? And it turns out that this can also reduce the chaos and thereby improve the flow. But things would get even better if we would basically induce something like a rotary flow, as we do over here. Okay, now basically, you could think of a systematic optimization of pedestrian facilities and say you have a certain architectural plan that would be your original, then you would multiply that plan and would make some modifications, so-called mutations. Then you would do test runs in order to see how well those different architectures work for the pedestrian flow. So there would be evaluation criteria, performance criteria, such as efficiency, which measures basically the actual average speed into the desired direction of motion divided by the desired speed. Then you select the better solutions, multiply them, mutate them again, and you do that many times until you don't have any improvement in them. And if we do that, for example, for such a situation of a room with an exit or a corridor, a bottleneck in other words, then due to the random mutations, you get all sorts of crazy configurations in the beginning, but eventually you get those funnel-shaped solutions, right? That make a lot of sense. In fact, here it's actually convex funnel. And we've also done some simulations where basically we have micro obstacles that could then aggregate to form bigger obstacles in order to help avoid the clogging phenomenon that you see over here. We'll go into the details later on. And so what turns out is that it's helpful to have either such a zigzagging solution, or you have an asymmetric solution. And why is that? Because basically these solutions absorb some of the pressure in the crowd, and that would avoid the clogging at the exit. More to come. Okay, so in fact, some time ago, we came up with this zigzagging solution shown over here, which should break down the pressure in the pushing crowd. If people reduce the pressure, in other words, in order to avoid terrible accidents from happening if people happen to push. Now the question is how theoretical versus how useful are those models? And it turns out that in the meantime, the social force models are actually being used by quite a lot of pedestrian simulators that are being used by architects, by crowd management, by people who plan big events, international events. Over here, you can see that the model has been adapted in such a way that people will walk around corners well. What you need to avoid is that they all cut corners and then basically create a congestion that is not natural. It also need to be able to simulate the evacuation of a hotel, both on a single level and on multiple levels. So you also need to take into account staircases, kind of 2 plus 1-dimensional simulations, so to say. And that can be done as well. And you have also to simulate route choice, because it could happen that there would be a bottleneck and therefore congestion forming, and people should actually use the alternative routes. They should use the alternative routes, and here is an alternative, and you will see that it takes a long time in this simulation until somebody figures out there's actually an alternative. So everyone is being queued for a long time over here, and everyone is losing a lot of time. This should be the case. So basically you need to add a route choice model that takes into account not just distances, but actually walking times. So now finally somebody notices there's another route. And of course that should happen much earlier. And in fact over here, a route choice model has been added that takes into account the waiting times. And now you see they're noticing much earlier that there is actually an alternative. Yes? If it's blocked?
If it seems from up there that it could lead to the design, then you go there and it's closed off. Go around.
Well, it assumes over here that people do have sufficiently accurate information. Of course, there could be situations where people get trapped and because they don't see what is really the situation around the corner. Yes. It's actually not an attraction-based force model that's being used for this, but it's a choice model, a multinomial logic model. It has utilities, and the utilities depend on the waiting sometimes.
Do you think here, technology
I don't deny that psychology does play a role sometimes.
because, yeah, I was just trying to relate it, for example, when you are doing that shift, but might not be good. You try to run there, and people who are behind you, they stop following you. But they realize, okay, you have to go back. Just make a little chaos because everyone is following someone, and it happens with a lot of us. And it's a sort of thing. Without
Sounds like a nice project for our agent-based course next semester. Yeah. Now the issue, of course, is simulation speed. If you have a lot of pedestrians, it could be actually tens of thousands or hundreds of thousands, big events. The Hajj even involves 2-3 million people. Then simulation speed matters, and you'd like to have an approach that scales linearly with the number of people. Of course, the potential interactions are expected to be growing quadratically with the number of people, but as it doesn't matter what happens far away, basically, you can make it more or less linearly by neglecting far away interactions. And in the meantime, simulations look like this, pretty realistic, three-dimensional, fully realistic. The latest version even has more elegant movement of pedestrians shown. But it's multimodal traffic scenarios that are now being simulated with pedestrians, public transportation, perhaps even logistics added. And you could look at scenarios with a lot of people. We'll fill that event location suddenly because we're actually interested in how long does it take to evacuate this place. Now you see, really, this involves a lot of people, and these kind of simulations are being done. Okay. So more take-home messages. I think we'll skip through this quickly. Or do you want me to go into this? Maybe we should end up on cloud disasters that are, of course, to be avoided. And unfortunately, sometimes these disasters happen. But a lot of insights have been gained in past years. So in principle, the knowledge that could help to avoid those terrible accidents has increased. And so hopefully that would make events safer. Now the scientific puzzles are, why do crowd disasters happen even if nobody wants to harm anybody else? Do you have any idea? Yes? This is what people often think. But if you then observe how people behave, you would be surprised how caring a lot of people behave. Not everyone necessarily, but people are by far not as selfish as we are often told. This is a very interesting point, and basically as a physics perspective on what could cause trouble there. In fact, we'll come to this point of systemic instability, which is very important to understand the phenomenon. Cascading effects or domino effects, these kind of things. So another question, are crowd disasters a result of people who start panicking for every reason, or Now, as one colleague basically formulated, are people dying because they panic, or are they panicking because they're dying? Any idea?
Sometimes you just panic because you see someone dying, but you start panicking. You are dying.
Here is the next. That would be a psychological cascading effect, yes. It's panicking, I would say, is a psychological phenomenon. Where people feel panic and start to behave in a unreasonable, relentless way. And it's often the perception of like what media report is this idea often that people panic, and that's, you know, they blame the people for what happened in many cases. And our research basically suggests that in most cases, this is not the right way of seeing the cause of the problem. So eventually we got interested in this phenomenon of panic because it happened again and again and again. We were asking ourselves, why is that happening? And so we assume people would get a bit nervous, would behave a little more, little less regular. So we increased the noise basically in the fluctuation term. And what we found is that the lanes of uniform walking direction broke up because of the noise. They were not anymore stable. And then two blocks of people developed that were confronting each other and blocking each other. And this is actually what is sometimes observed. Another thing that we basically found in the literature was that in many cases, not all emergency exits were being used in an evacuation scenario, say fire, event of fire. And then we came to the conclusion that it's herding behavior that does matter. And people tend to orient at what other people do because they think, oh, perhaps they know better, they know where the exit is. And so if they're following each other, they may not use all the exits in an efficient way. In fact, we've even done experiments. These are experiments that have been performed in Japan by a colleague of mine. Here we basically found that people, they don't see, because that is the situation that often occurs in a smoky environment, that you can't even see your own hand because it's such a dense smoke. If they can't see, then basically they would try to first find a wall and then move along the wall. And then if somebody else is there, they would tend to follow other people. So if you see the exit, then obviously everyone is just walking there right away. While if there's no visibility, or we simulated that by blindfolding people, then they walk towards the wall and some collective behavior would come about, and there could be faster, slower effects and so on. Now, of course, crowd disasters should be prevented first of all. And we've been doing a couple of case studies. Among them, we've been looking into what happened during the Love Parade 2010, where a crowd disaster unfortunately happened in Germany. And this was the festival area. So there are these trucks, the music trucks, so-called floats that move around. And this was a tunnel through which people had to get onto this area. There were some ramps connecting the tunnel with that area. That was the main ramp. Things got crowded. Police put some police cordons in the way in order to stop the crowd. That didn't work for a long time. And eventually everything got out of control. If you want to know details, and have a look at the paper. I think it has a lot of details in it. That's the paper. And basically, we come to the conclusion that there was no single cause of that crowd disaster. There were many factors that contributed to the crowd disaster happening. There were error chains, different factors added to each other or multiplied even each other. Nobody was guilty alone for this happening. Everyone could have made a change towards the better. There would have been many ways of preventing that crowd disaster. But in order to understand what could have been done, it's helpful basically to reconstruct what caused what. So this is a causality diagram in a sense, how different events triggered other events. And in the end, it was a amplifying feedback cycle, a circulus viciosus, you could say, basically that the situation get out of control. Unfortunately. Have a look at this. I think it's really a very interesting case, a very tragic case. Sachit, are there any new questions or comments now? And then the question is, what can you do basically to prevent those crowd disasters? And here just a few points. So it turned out that it's not a good idea to put too much political pressure on the organizers of such an event. Evacuation studies must work with realistic numbers and should not be restricted to special cases such as evacuation scenarios. The team of people doing the assessment should be allowed to ask also additional questions. Very important point, actually. Crowd management and security concept must consider sufficient safety margins, reserves in a sense, right? You need to have contingency plans. Bottlenecks must be avoided or mitigated. Dense counterflows or intersecting flows are to be avoided. Unavoidable bottlenecks or confluence points are to be monitored. And security forces and emergency units must be in the immediate neighborhood. Contingency plans must exist and must have been exercised. Communication is extremely important. If communication doesn't work, like the walkie-talkies, for example, don't work, as it happened over there, then coordination basically is destined to fail. And it might be a good idea to have experienced national or supranational professionals to support local organizing teams when it comes to the organization of large events, right? Here are some tables that go into more detail. So it says, if you observe this, then that is the kind of situation you're confronted with, and that is the required action that needs to be taken. So, for example, if jams of people are forming and growing, then there's insufficient outflows that may cause serious problems over time. communicate with the crowd, promptly take appropriate flow reduction measures such as redirecting people, and so on and so on. Stop and go waves occur. The continuous flow has broken down, the outflow capacity is considerably reduced, the situation may escalate quickly. Take suitable countermeasures. Pressure relief strategies should be taken and people informed about them. Before any obstacles in the way must be removed, a sufficient number of emergency units and police must be in the critical area and ready to take over control in interaction with the crowd management and so on. And things can get worse and worse. You know, people cannot move freely and are squeezed between others, or people disrespect fences or try to get out of the area. And that was totally misinterpreted in that case. It basically should have told the responsible crowd management and police that the situation was critical and likely to get out of control. And finally, crowd turbulence might occur. People may scream or shout for help. Injuries and fatalities are likely. A crowd disaster can happen anytime. And then you have to calm down the crowd and guide it, continue to evacuate people, and so on and so on. And even more, two more steps. And here, for example, immediate help and first aid are needed. Probably for many people, hospitals must be prepared to shift from routine to large-scale emergency operation. And only here, people behave relentlessly, and not everyone, but some of them. People crawl over others. That is really very extreme. And a crowd disaster has probably happened. Maybe hard to see, but that's a sign of it. And here, rules for a state of serious emergency need to be applied. Okay. Had this table been available and applied at that time, probably that could have changed the situation. Yes?
How long does it usually take to go from like situation 1 to 6? Like is that in a matter of seconds or is that big?
No, it's not seconds. In the crowd disaster that happened, I think it was 2007 at the Hatch, it took about 30 minutes between the stop and go waves set in and the crowd turbulence that then caused the falling of people and the crowd disaster. So there were 30 minutes of time. That could be less. But if you see the stop and go waves, then this is basically an advanced warning sign and tells you, oh, this is going to be critical shortly. If you don't respond immediately, then things would probably be too late. So it's the situation, if the outflow is smaller than the inflow, changes quite quickly because the density would increase in a short time, and that would make everything critical.
Is there anything you can do as an individual in the crowd, or is it entirely on the organizers?
First of all, it's easy to say, but it's really important to keep calm and to be respectful and helpful to other people. That can make all the difference. In the case of the laugh rate disaster, communication didn't work. But there were people standing besides the ramps, kind of elevated, and they were giving signs to the people who couldn't see what was going on. So yeah, people were trying to help each other. First of all, to orient about the situation and what they could do in that situation. But I think more effective communication could have made a huge difference. What we then did over here, in collaboration with another team you may know, the team of Professor Hulscher, is we did large-scale simulations, also using virtual reality approaches. And we were basically looking into different kinds of scenarios. That is again the location. And we were looking into, for example, situations where police fences were used to stop the crowd, and other scenarios where police fences were not used, plus some other variations of the setting of the crowd management approach. And all of these situations were then simulated in order to compare the effectiveness, the density, level of congestion, criticality. And it turns out that, in fact, the police cordons were not very good for the outcome of the event, to say the least. So basically, it was not unavoidable that a crowd disaster happened. Now, we know this now from today's perspective. Of course, the insights gained should help prevent future crowd disasters in other places. I hope that study, besides others, will be read a lot, and in fact has already been read a lot. And there's also some new pieces of technology that are becoming available. So, for example, in the Socionical project, colleagues of mine, Ulf Blanke and others, Volukovic, for example, they've been assuming that people would have a smartphone app that would deliver some data, not directly to the police, but there would be an aggregation service that would make sure that no private data would be revealed about the trajectories of individuals, but data about speeds and densities would become available to the police and crowd management. In this way, depending on the density and criticality, people would get feedback. So they would benefit from the sharing of data of themselves and others by getting advice on what to do and what better not to do, and what would be safer routes. So that's the situation that the police would see. They would have different monitors to give them insights. And so here it's assumed that there would be a congested subway station, and that's not a good thing. So the app basically delivers a message and says, okay, congestion ahead, please take this other route. And it has been actually applied in many events in the meantime. Okay. Yeah, I think this is the point where we can stop. The end of my lecture. Are there any further questions or comments? Yes?
So these crowd disasters are like case studies where we go from stage 0 to like stage 5, but then instead of going to like stage 8, next study.
If there are some case studies where it was possible to prevent the
Yeah, so instead of going like that, the disaster sort of comes back and stabilizes.
I'm not sure there are many of these studies. I think most people have become interested in studying the cloud disasters, but it's a good point actually. The issue, of course, is that you cannot make experiments with people in risky or dangerous situations. But that's why we use the virtual reality environments to get some insights into situations that you could not study in.
The situation's not even recorded because they're not interesting because it doesn't have a great disaster. For example, at a festival, there might be a brawl. There is, it goes to stage 5, stage 6, it all calms down and then it's over and it's analyzed because no lives were lost or something like that.
It's yeah, there might be less interest of scientists in looking into this kind of data. I guess in principle it should be available in many events, but would be in fact an interesting new study to make, I guess. All right, so thanks a lot for joining. I hope that was an interesting lecture for you, and I look forward to seeing you again next week. Bye-bye then.